Hi everyone, welcome to this first video where today we're going to be looking at what are algorithms, and this is the first video in a series of revision topics covering the new 9-to-1 GCSE Computer Science for the AQA specification. So in this video we have a set of learning objectives which we're going to be covering. We're going to be looking at explaining the terms algorithm, decomposition and abstraction. We're going to be looking at using systematic approaches to solving problems through the creations of pseudocode and flowcharts. We're also going to be explaining algorithms in terms of their inputs, processing and outputs, and we're also going to be looking at determining the purpose of simple algorithms. Throughout this video we have many points, key learning points, supplied by AQA which you might want to take note of, as this might help you with your exam revision and essentially with your exams. So first of all, we need to think about computer science itself as a topic. So computer science is based on many principles. It's based on architecture, programming, number systems, but one of the main principles of computer science is the use of algorithms. Now, you need to know this, but an algorithm is a sequence of steps that can be followed to solve a problem or to complete a task. The way round you get it, essentially it doesn't matter, but you need to have the gist that it's used to solve a problem or task of some sort. Now you need to know that algorithms are not computer programs, but rather a computer program such as a Java file or a Python file. It's an implementation of an algorithm. So when we look at algorithms, we need to know an algorithm is a sequence of steps that can be followed to solve a task. In this, we could be looking at making a cup of tea. Here we have a flowchart on how to make the perfect cuppa. Placing a tea bag in a mug, boiling water, pouring it over the tea bag, then we ask, is it strong enough? If it's not strong enough, we ask again, is it strong enough? Until it is strong enough, where we remove the tea bag. We might add the milk and stir it, and then if it's cool enough, if it's not cool enough, and then we drink it. And that is the algorithm for making a cup of tea. But if we put this into consideration, is this the official or maybe the only way, like the only number one solution to making a cup of tea? Is everything in the flowchart a necessary thing? Well, for example, some people may not be so bothered about how cool their tea is. In other cases, some people might not even have milk whatsoever. And as is many debated times, milk might be added before the water. Controversial, I know. But we need to put this into context of solving a problem. So algorithms are used to solve problems. We need to know that algorithms can be used to solve more than one problem. In the context of the cup of tea, people's opinions differ on how we make tea. Some people leave the bag in for longer, some people put the milk in for water, some people don't even use milk. But still, solutions, many as there may be, they can be obtained through many different methods. The exact same principle applies to the use of algorithms. Many solutions can be used to solve one algorithm, and an algorithm can be used to solve more than one problem. Now when we look at representing algorithms, you'll see on the last slide we used a flowchart. This is like a visual representation of the flow of data in an algorithm. When we look at representing algorithms, we can use a flowchart like that, or we can use pseudocode. Flowcharts, as I said, they're graphical representations of data flow using symbols. So we have terminators, that's sort of the start-stop, processes, so this might be assigning a variable, it might be maths. We have the decision diamond, so if we need to ask a question, that's what's asked in the algorithm, and the arrows indicate the flow of the program, and we also have connectors in case we need to go off page. We can also use this symbol when we want to refer to a document, and this for a subroutine. We can also use inputs and outputs. Now looking at pseudocode, pseudocode is a representation of an algorithm using standard English. It's used to resemble a high-level programming language such as Python. So here we have an algorithm for converting from Celsius to Fahrenheit. So this first line of code here, we ask the user for a temperature. Now the temperature is in Celsius. Now our new temperature is calculated as being 1.8 multiplied by our temperature and then adding 32. We then output our new temperature as our answer. Now this pseudocode here doesn't exactly follow the AQA standard or the AQA convention. If you want to find out the AQA convention for programming, I'll leave a link in the description to the pseudocode guide. It's really useful and I would definitely advise reading it over before you go into programming, or maybe even to your non-exam assessment. And in Python we would use this pseudocode. This code here would be represented as this in a Python program. As you can see, output has a different the syntax is different to the pseudocode, but the principle is the same. New temperature, obviously, the line remains the same because that's what it is, but user input, it's different to the syntax in Python, but the principle is the same. So when we look at designing solutions, we might say that we want to write pseudocode and draw a flowchart to design the solution for a problem. So we might want to calculate how much it will cost to see a film where an adult is £11.10, a child might be £9.10. If the child is under 5, they don't have to pay. So using our problem solving skills and an algorithm, we could write this by analysing the requirements. So first of all, we would get the number of adults and children. I always think it's very useful to, even in your non-exam assessment and in any problem, you want to analyse the requirements of the program. So if we go back here, how much will it cost to see a film where a singular adult is £11.10 and a child is £9.10? Well, we're given this in the context that we have any number of adults and any number of children. So we would start off by getting the number of adults and children. If there are children, we know that if a child is under 5, they don't have to pay. So if we have children, we need to ask how many of them are under 5 years old. Once we've got that, we can apply the discounts. And after that, we can calculate the total cost of the ticket. So when a total is asked for, we can use something called an accumulator. And this is a value where it increases when more needs to be added. And this is stored in a variable. So our pseudocode solution, first line, obviously we might write this in a function, which we could call ticket prices. We can then say that the total price at the moment is 0. So we set the price to 0 so that when we calculate values of an adult and of a child and any discounts, we can add that. We then ask, how many adults are there? And I know the convention here is sort of flipping between Python syntax and pseudocode, but the principle applies. So we ask how many adults there are, and then we ask how many children there are. So these values are attained from the user. If the number of children entered is greater than 1, then we would say that a discount is asking how many children are under 5. And then the total price is the number of children that we have minus the discount multiplied by 9.1. And obviously this 9.1 value represents the price of one child. So the number of children that we have, subtract the number that are under 5. So if there's one child that's there and he or she's under 5, then subtract that. 0 times 9.1, so nothing added. And then we end that. So it applies a discount. And then our total price, we add the number of adults multiplied by 11.1. So if there are 2 adults, that would be equal to 22.2. So we calculate our total price, which is added on to the number of children price. And then we can print our total price. Now, one thing I've just noticed is that one line, I've messed it up a little bit. If number of children is greater than 1, well, obviously if there is one child, you know, so it just shows that everyone's infallible. So, well, everyone's fallible, rather. Anyway, moving on. So when we look at designing solutions, we could draw a flowchart. So the data in an algorithm to calculate the perimeter or the area of a rectangle. So we analyse our requirements. We need to calculate the area and the perimeter of a rectangle, but we must allow the user to choose which one they want. Note, or. That's a key word there. Always look for the key words such as and, or. So our solution here would be that we would start off. So we start off by getting the width and the height of the rectangle, because whatever happens, we're going to need that. After that, we need the user's choice. So are they going to calculate the perimeter? If they're not, then our answer is the width multiplied by the height, which is the area. If they do want to calculate the perimeter, then it's 2 lots of the widths and 2 lots of the heights. And then whatever the result is, the answer is then printed out. So when we're looking at the flow of data flow in the systems, they use inputs, processes and outputs. Now we can represent these using trace tables, so we can show the inputs and outputs at each line of a program. We see these as simulations for an algorithm, so they can be used to demonstrate sequential and modular programs. So for example, trace tables are used to simulate how a code would run using different values. So this is a counting algorithm, where we say x is 1, we then print x, but while x is less than or equal to 3, then y is 5 lots of x, and we're going to print y. Then we're going to print done. So in this trace table, we're using test values, and that's not very clear. It will be a bit clearer for the next videos, but we're using test values of x as being 1, 2, and 3. So when x is 1, our output is 1 and y is 5. When x is 2, y is 10, the output's 10. Once the output is 15, when x is less than or equal to 3, we're done. So that's essentially using trace tables. So if you want to have a go at stuff yourself, you can look at what algorithms are, and this is sort of useful for notes. So you can define an algorithm, you can look at 2 methods in which algorithms can be represented, and using this video, this is good revision notes. And then if you want to have a go at looking at pseudocode yourself, you can design a solution to the scenario where you need to write an algorithm to check if someone's legally able to drive. So the legal driving age is 17. And then you can use a trace table for the algorithm using test values of 15, 17 and 19. And that's all for this video. The next video we're going to be looking at searching and sorting algorithms. So thank you for watching, and I hope you watch next time.